All right, hello everyone. I'm very excited to be here with you to talk about our research projects and let me get started. So our motivation for research is to develop a computation musculoskeletal model for people with disabilities. And we are also developing exoskeletal and prosthetic device for these impaired individuals to provide better functions of walking. And also we are developing ubiquitous kinematics and kinetics monitoring system using reduced number of sensors like IMU sensors using machine learning algorithms. So these are the main research topics, what we are conducting right now, and I'm going to go one by one detail. So the first of all, in order to understand my research, we need to understand the mechanism of Achilles tendon and muscle. So this is the musculoskeletal model, what we are using, and this is a free software. It's called OpenSim. And when we walk, this is a calf muscle and Achilles tendon. And Achilles tendon is almost similar to the mechanical spring. So when we are walking, the gastrocnemius, which is calf muscle, is holding the Achilles tendon and the Achilles tendon being stretched. Okay. And then the stored energy returns when people walk, so that it provides the propulsion and support. So this is the way that we can walk in a very, very energy efficient manner. But unfortunately, the lower limb amputees, especially below knee amputees, their calf muscle and Achilles tendon mostly gone, but only the gastrocnemius, which is calf muscle, remains. And then when they walk with the prosthesis, the residual muscle will play different roles compared to the intact muscle. And this is the question, how the muscle is going to contribute to walking. So this is a very typical surgical method for lower limb amputees. And as you can see, the intact muscle provides a knee flexion and ankle plantar flexion that is useful for propelling body forward. But unfortunately, the lower limb amputees, they don't have any propulsions. So we need to provide some assistance for these type of populations. So in order to figure out the function of residual muscle, we need to do these steps. So as you can see, the milestone 1 is to figure out the characteristic of residual muscle. And the milestone 2 is to figure out, to develop assistive device that is provide different tuning parameters, because ultimately we want to use this the musculoskeletal model and assistive device. We want to modulate the function of residual muscle, so that if the residual muscle negatively impact walking, then perhaps we can alter the function by using the neuromuscular sensory feedback. So first of all, we're quantifying the muscle momentum, which is the muscle pathway. And as you can see, we're using ultrasound and the motion capture system. And then using this motion capture system, we can identify what is the center of the joint. And then using the ultrasound, and then we can drag the muscle. And then from the ultrasound image, we can see the cross-section area of the muscle. And then from the cross-section area, we gather all the trajectory of centroids. And then from the centroids, now we be able to figure out what is the muscle pathway. And that is going to be used for lower limb amputees in the future. And then in order to accurately present the muscle pathway, we are using optimization algorithms to generate the wrapping object that is constrain the muscle, the pathways. And later, we will also need to figure out what is the active component of the muscle. So this is one participant who were recruited in our the project. And basically, this is finding what is the active component of the muscle. So we measure the electromyography, which is electric signal from the muscles. And also we use ultrasound so that we can find the length of the fascicle length when the muscle generates maximum activation, electric signals. And then later, we also need to find what is the muscle stiffness and what is the muscle slack length. And that is very challenging unless we take out the muscle and then install on the universal testing machine and then place it back to the human body. Almost impossible. So we determined to use the optimization. First, we place the participant on the human dynamometer, which can measure the joint torque. And then while the participants sit on the human dynamometer, all the muscles were stretched, and then we can capture what is the joint torque, which is generated from the stretched muscle force. And then from there, and then we bring into the musculoskeletal model, and we randomly change the muscle parameter because we want to figure out what will be the muscle stiffness and muscle sag length, which is the redundant system in musculoskeletal model. So we use optimization algorithm and we estimate the parameters using this optimization algorithm. And then we also did a very thorough validations that replicating the 101 scale, the human body with aluminum profiles and spring. So we were able to get pretty accurate estimate, which is errors were about 3% to 4%. And then later, we also need to develop a prosthesis that can provide different functions. So actually, we are providing the different types of assistive device like this. So you see the left upper corner, we're developing a ankle orthosis that is assistive device for people with neurological disorders, such as children with cerebral palsy or the stroke survivors. And these devices were providing the level of stiffness because the adjusting stiffness is the major parameters for this type of ankle orthosis. And the top figure is using 3-bar and 3-point bending mechanism. And the bottom part is we integrated the unique the function of mantis shrimp, and the mantis shrimp is the sea creature, and then it creates a huge amount of force onto their 4 appendages. And the secret behind is they are using the saddle spring that allows the mantis shrimp to create a huge amount of energy return, energy store and return. And so we were very amazed about this, and then we decided to implement this saddle spring onto the ankle orthosis. But in order to change the stiffness, we figured out that changing the curvature, by changing the curvature, we can change the stiffness. So we are using design optimization algorithm to figure out what will be the optimal curvatures to maximize the range of stiffness and also to maximize the energy return. And then that is also applied to the other bio-inspired high energy return processes. And those concepts are pretty similar. And we are also developing pneumatic and hydraulic hybrid processes. Although there are some active processes out there, but unfortunately, the actuators are not work with the passive component. So the benefit of this design is it can fully utilize the passive elements. So if you can see, this is a carbon fiber blade, and this is hooked up to the pneumatic cylinder. So as pneumatic cylinder, the oil in pneumatic cylinder is incompressible. So when the carbon fiber beam is bending, and then by simply closing the valve, then we can capture the deformation, the energy from the deformation of carbon fiber beam. And then this force is transmitted to the pneumatic system. And then in the pneumatic system, the motor is going to rotate the cam, and the cam is going to give extra compressions so that the device can store even more energy. And then when the energy is needed, when people try to push off their body force and supporting body there upward, and then all the energy is going to be released. And we believe that this is going to be the new paradigm of the lower limb prosthesis. And this is another project, which is the capturing the energy storage on the commercially available carbon fiber foot blade. The reason why we come up with this design is although the carbon fiber blade is stored and return energy when people walking, But unfortunately, the energy release timing is so fast, so there's not much energy left when people trying to push off their body forward. So so we decided to develop a very simple ratchet gear mechanism. And then when the prosthesis carbon fiber beam of prosthesis maximally bent, and then we can store and we can capture that energy until it's needed. And then the next research topic is ubiquitous real-time walking function analysis. And this is a figure what I took when I was postdoc in University of Michigan. And when people walk with a prosthesis or assistive device, they usually walk on the straight walking surfaces, and then the clinicians evaluate whether the participant walked good or bad, and then based upon how they walk, they tune their device. But the problem is usually sometimes people are feeling the pressure, so they walk very nicely, but after they discharge, they may walk differently. So we need to monitor how they walk, whether they walk good or bad. And in order to evaluate their motion is very challenging, because typical motion capture system is spatial and temporal limited. So that's why we develop a machine learning algorithm that uses the two IMU sensors on the foot, and then figure out what will be the joint angles and the joint torques. And the benefit of this algorithm is we can monitor how they walk, and then what's the joint torque in their daily living. And eventually this can be utilized for the construction workers and elders, or other, the people with disabilities. And this is another the case. So our algorithm is just not using the LSTM. Rather, we customize it, and we're trying to implement in the physics informations to the machine learning algorithm, so that we're trying to make the machine learning algorithm is interpretable, and also it can provide the accurate estimates even when the absence of the input data. And also, this is an ongoing project that is reconstructing the visual sensory feedback to control the prosthesis. So basically, when we walk, we are using visual sensory feedback. So we look at what will be the upcoming obstacles or upcoming walking condition. And then this visual recognition information transmitted to the spinal cord. And the spinal cord, once it's engaged to the new walking conditions, and it gives the immediate response to the muscle, so that we can walk in a very natural movement, even if we walk in very different walking conditions. But unfortunately, prosthesis users, they have disconnected between the neural control and the prosthetic control. So their motion often very awkward when they have different walking conditions. So we're using IMU sensors and the machine learning algorithm and wearable cameras to detect what will be the upcoming walking condition. And then the IMU sensor is going to calculate, what will be, how much force and how much the energy should be returned to the prosthesis, so that people can manage very natural walking in the future. So as you can see, my near-term research plan is to fabricate all of these assistive devices, and then also developing the even better algorithms, and conducting more experiments to get more conducting experiments to get better data. So to do this, I need to collaborate with many different areas in expertise, such as people who are working in orthopedics, physical therapists, and also I'm seeking machine learning experts to develop even advanced machine learning algorithm that can provide very accurate estimate of joint kinematics and kinetics. And this is my long-term research plan. And also, I'm interested in doing the advanced prosthetic and orthosis control that can provide neuroplasticity rehabilitation. And also, I'm interested in analyzing the impacts of different tuning parameters of prosthesis to people who are treated with osseointegrations. And also, I also want to develop an algorithm for minimizing the hypermuscle tone for people with stroke or cerebral palsy. And these are my collaborators and graduate students and undergrad students and funding resources. And I'd like to take any questions you have.